Energy balance for biosystem. Module 7 Conservation of energy. Segment 4 Calculation of enthalpy in non-reactive process. Ismi Lili from School of Life Sciences and Technology, Institute Teknologi Bandung. In the previous segment, we already discussed about the basic energy concept, review of energy conservation statement, closed and isolated system. And in this segment, we will discuss about the calculation of enthalpy in non-reactive process. The change in enthalpy can occur as a result of temperature change, a pressure change, a phase change, mixing, or a reaction. A state function or property is an intensive property that depends only on the current state of the existence of the system, and not on the path taken to reach it. Examples of state properties include temperature, pressure, composition, specific enthalpy, and also specific volume. In order to apply the conservation of total energy equation, we often need to calculate the values of internal energy or enthalpy. Enthalpy is a function of internal energy and depends on the same immeasurable processes. For this reason, the absolute values of internal energy and enthalpy can never be known. Specifically, the difference in internal energy or enthalpy between any two states can be calculated. The governing equations in segment 2 are constructed in such a way that the difference between the inlet and outlet energy rates or amount, not the absolute value of the energy rate or amount, is required. And the differential equation can be seen in this equation below. And for calculating the change in the rate of enthalpy can be calculated using the equation below. The definition for delta H dot in previous equation is critical because it offers a method to calculate the change in specific enthalpy as the difference between the inlet and outlet of the system. Sometimes specific enthalpies are given on a per mole basis. In this case, the change in the rate of specific enthalpy across a system can be defined as the equation below. For a system with a single input, a single output, and no accumulation, the mass conservation reduced to m dot input minus m dot output is equal to 0. And the previous equation also can be written as the following equation, where specific enthalpy is given on a per mass basis. The change in the rate of enthalpy can also be written as the mole basis. The change in the enthalpy of a system, or delta H, is defined as equation below. The definition for delta H in this equation offers a method to calculate the change in specific enthalpy as the difference between the input and output of the system. Since H hat is a state function, the path to convert a system from one state to another can be accomplished using the most convenient pathway or transition. For example, consider the specific enthalpy change from state A to state B. So the delta H from state A state B can be drawn as the equation below. The specific enthalpy at state A is HA minus H reference, and the specific enthalpy at state B is HB minus H reference. So the change in the specific enthalpy, or delta H, is equal to the H enthalpy in the state B minus enthalpy in the state A. To calculate enthalpy changes, we often need to develop a hypothetical path that transitions an inlet enthalpy condition to an outlet enthalpy condition. Best practice is to have one change along each step of the system. Usually, each step of the path in a non-reacting system has a change in one of the following, such as temperature, pressure, or phase. So the change in the specific enthalpy across the system is the sum of all steps in the hypothetical path and can be written as the equation below. In this part, we will discuss about the change in temperature. In a system, the energy transferred to rise or lower the temperature of a material is sometimes called as a sensible heat. This energy transfer is equal to the enthalpy change that occurs when a change in temperature occurs. For a system with a temperature change, the rate at which sensible heat is added or removed is equal to the rate of enthalpy change. Consider an open steady-state system with no changes in potential or kinetic energy and no non-flow work. The enthalpy in inlet minus enthalpy in outlet and plus sensible heat is equal to 0. Then the sensible heat is equal to the differences between the entropy, or Q is equal to the delta H. The specific enthalpy of a substance depends strongly on temperature. A temperature change, or delta T, leads to a change in a specific enthalpy, or delta H. And here is the schematic relationship between the specific enthalpy and the temperature. The slope is the line is the heat capacity at constant pressure. So the heat capacity can be calculated as the equation below, and also as the integral form. The delta enthalpy can be calculated using this equation, where T1 is the first temperature and T2 is the second temperature at constant pressure. And also for the solid and liquid in most biological systems, heat capacities are not a function of temperature. Therefore, the heat capacity for solid and liquid can usually be approximated with just the first term of equation, which is the heat capacity is equal to A. Since Cp is constant, so we can write the equation as the equation below. In this part is the change in enthalpy as a result of change in pressure. For solid and liquid, it has been observed experimentally that specific internal energy and specific volume are nearly independent of pressure. Therefore, we can write the calculation as equation below. And for ideal gases, the specific enthalpy doesn't depend on pressure. Therefore, we can assume that delta enthalpy specific is 0 when considering change in pressure. And in this part, the change in enthalpy as a result of changes in phase. Phase change are accompanied by relatively large change in internal energy and enthalpy as non-covalent bonds between molecules, such as hydrogen bonds, are broken and formed. In the liquid and solid phases, water molecules are more densely packed and are held together by attractive forces between the molecules. And in the solid phase, they have little rotation or freedom of motion. And here in the table 4.2, the specific enthalpy of water at 100 degrees Celsius and 1 atm is different for saturated liquid phase and also for saturated vapor phase. The specific enthalpy change associated with the transition of substance from one phase to another at constant pressure and temperature is sometimes known as the latent heat of the phase change. The latent heat of vaporization, or delta HV, is the specific enthalpy difference between the liquid and vapor forms of a species at a given temperature and pressure. And the latent heat of melting or fusion, or delta HM, is the specific enthalpy difference between the solid and liquid forms of a species at a given temperature and pressure. And also, for the latent heat of sublimation, or delta HS, is the specific enthalpy difference between the solid and vapor forms of a species at a given temperature and pressure. And the transition between liquid and vapor, solid and liquid, and solid and vapor are summarized in the table below. And in this part is about the change in enthalpy as a result of the mixing effect. In ideal solution or ideal mixtures of several compounds, the thermodynamic properties of the mixture are a simple sum of contribution from the individual component. In mixing real solution, bonds between neighboring molecules in the old situation are broken, and new bonds between the mixed components are formed. In this solution, a net absorption or release of energy usually takes place, resulting in a change in the enthalpy of the mixture. The heat of solution, or delta H solution, is defined as the change in enthalpy for a process in which 1 mole of a solute, it can be gas or solid, is dissolved in a specific amount of a liquid solvent at a constant temperature T. The heat of mixing refers to a situation when two liquids are mixed, and the calculation for the enthalpy change for the mixing of two liquids is similar to that described for the heat of solution. And in the most biological process, significant change in enthalpy due to heats of mixing and heats of solution do not occur. And for the next segment in the next module, we will discuss about the open steady-state system, no potential or kinetic energy changes. Until then, I'm Lily from Institute Technology Bandung.